Hi, in this video we'll be discussing position, velocity, and acceleration according to graphs and how we can use calculus to figure out the position, velocity, and acceleration of particles, objects, cars, vehicles, etc. Let's get to it. So, taking a look at these graphs I just made, the first graph on the left represents a position versus time graph. So, according to whatever time that we might choose, this graph shows what the position is of a certain particle, vehicle, car, whatever, at a certain time. The middle graph shows its velocity at that same time. And then the third graph shows the acceleration. Now, what is position? Position is simple. Where are you? What's your distance? Velocity is distance over time, or more specifically, displacement over time. What is your change in initial position and your final position, and how long did it take you to get from your initial position to final position? That's your velocity. You might see this in, say, your speedometer. You might show it in miles per hour. In physics, you might use it as meters per second. And then acceleration. Acceleration is change in velocity. So it's basically you speeding up or slowing down. So you go from 20 miles per hour to 30 miles per hour, or you go from 30 miles per hour to 10 miles per hour. You're accelerating, meaning you have a change in velocity. So we can use a position versus time graph to figure out its velocity and acceleration at different points. And let's say we don't even have these graphs, we just have a function. Let's say a function of position versus time. We can use that to figure out velocity, acceleration, of course, using calculus, and even figure out different characteristics of the graph, helping us sketch it, even without, using a calculator or Desmos. Now I want you to notice something here. The position versus time graph shows a seemingly, I'd say, a quadratic function. Okay, this is just quadratic from x equals 0, or sorry, t equals 0 all the way to t equals infinity. So we see that its rate of change is not constant, right? Because it's a quadratic function, its rate of change is always changing. Now, if we take a look at the same velocity versus time graph, though, that is linear. The velocity is always increasing at a same rate. And then, as a result, since it's increasing at a same rate, then we say that this is the acceleration versus time graph, and the acceleration is constant. Since its change in velocity is constant, the acceleration is also constant. X of t equals 3t squared minus 6t plus 4. This function here represents the position of a particle moving along a straight x-axis. Okay, so let's say this is an x-axis, this is 0. Then let's say at t equals 1, I'm not going to go and solve for it, but let's say at t equals 1, the position of the particle is at this value x of t. So this basically spits back what is the position of the particle. Now, if we were to take the derivative of this, so now we take x prime of t, we can use power rule, 6t minus 6. This gives us the velocity of the particle at whatever point t that we might choose. If we take the derivative again, x double prime of t, then we get a simple 6. Okay? So this goes back to the initial thing that we saw. So let's say that this is 3t squared minus 6t plus 4, and I know that doesn't really represent since the y-intercept is at 0. But let's say for argument's sake it is. Then if we were to take the velocity of this position function, then it should be linear. It should be linear according to what we see here. And it is. When we take the derivative of it, 6t minus 6, this is a linear function. And then we see here that the acceleration is a constant, just y equals something. Y equals a constant, and in this case, the constant is 6. Now, using this, even if we don't have those graphs, we can really use this to help us make a sketch of the graph. How can we do this? Well, let's take a look at the position function and the velocity function. So whenever you want to look at a changing point, okay, where a function its slope is positive, but then it turns negative. That turning point, as we call it, how do we calculate that? Well, let's take a look at a simple quadratic function like this. The turning point is obviously right here at whatever point that is. Now, if we were to make a line tangent to that like so, you'd notice that its rate of change is 0. It's 0. So if we don't have a graph and we only have its function, then what we want to do is to figure out where the graph has a turning point. We'd want to set its derivative equal to 0, its first derivative. So let's do that. So we do 0 equals 6t minus 6, 6 equals 6t, and that leads to t equaling 1. So that means that at t equals 1, this quadratic function, it has a turning point. Then I've constructed a little number line here, which is meant to represent the values of t for the derivative of x of t. So as we've shown, the turning point for the particle, for the position versus time function, it's at t equals 1. Now what we want to know is between 0 and 1, and I'm using 0 because t represents time, and time can't be less than 0, you can't go back in time. But it's between 0 and 1, and we want to know if between 0 and 1 is the rate of change negative or positive. In other words, is the velocity negative or positive? Now, some people might confuse that having a negative velocity automatically means that you're slowing down. That's not true. It just means the negative sign, it represents direction. The magnitude is what represents speed. You got to remember that. Magnitude represents speed. The sign, whether it's positive or negative, represents the direction. So you want to keep a good note of that. Now, why 1? Because as we've shown, 1 is the turning point. If before 1 it's negative, then after it has to be positive. If before 1 it's positive, then after 1's got to be negative. They both can't be the same, or else it's not a turning point. So let's take a look at this. How will we do this? Well, we'll just use a little testing point. Let's say 0.5, and for here we'll say 2. Very simple. So plugging in 0.5 to the x prime of t, let's say 6 times 1/2 is 3, minus 6 is negative 3. So I'll just erase this, and since it's negative, I'll put a little negative sign there. And for 2, let's see here, 6 times 2 is 12. 12 minus 6 is 6, so that's positive. So I'll put a little positive here. Now, remember, negative, positive, they don't represent speed, they represent direction. So really, this means that from 0 to 1, the particle is moving to the left. And from 1 onwards, it's moving to the right. Now that we've asserted direction, now we want to know, is the particle speeding up or slowing down? And for that now, we have to look at between velocity and acceleration. Take a look at this. This is a little chart that I made, and the top row represents velocity and the bottom row represents acceleration. Now, if we calculate the velocity to be positive, but we find the acceleration is negative, then that means that the particle is slowing down. So I'll use a little down arrow to represent slowing down. In the same manner, if velocity is negative, but acceleration is positive, then again, the particle is slowing down. If both signs are opposite, it's slowing down. They cancel each other out, basically. If velocity is positive and acceleration is also positive, it's going up. It's speeding up. So we put a little up arrow. In the same manner, remember that I said, the direction is represented by the sign. The sign does not mean that it's automatically slowing down. We have to look at the agreement between velocity and acceleration and their signs. So velocity has a negative sign. Acceleration also has a negative sign. Therefore, it's speeding up. Let's look at this using a little example that I made. If we look at from each turning point, so there's a turning point here, 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 and here. And let's just say this represents a velocity graph. So we see here that the velocity is positive, so this will be 0 here. Anything up here is positive, anything down here is negative. This, remember, acceleration is the slope of velocity. It's a derivative of velocity. So if we look at from here to here, okay, just this little portion here, we see that the acceleration is positive since it has an upward slope. The velocity is also positive since it's above 0. So here we say that the object is speeding up, and that's true. As we go over by time, the the velocity increases. Take a look here from this point here to this point. The acceleration is negative because it has a downward slope. But its velocity is positive. It's still in this up region. It's above the x-axis, so it's still positive. So therefore, that the object is slowing down. Now take a look from here. At this point here, the velocity is 0. The particle is not moving at that point. It is changing directions though, so that's why. So imagine you're going, and then you gotta change direction. So you just temporarily slow down, and then you gotta change directions like that. So that's basically what might be happening there. Now, if we take a look from here to here, just this portion here, the velocity is negative. It's below the x-axis, and the acceleration is also negative. The acceleration is also negative since it has a negative slope. Therefore, the object is speeding up. Okay, both signs agree. Just because they're in the negative area does not mean that they're slowing down. It's just because it's their direction. It represents direction, nothing more. In this example here, it looks like it might be speeding up, but look, it has a positive acceleration. The acceleration is going upwards, but the velocity is 0. Not 0. It's negative. It's below the x-axis. Since velocity is negative and acceleration is positive, they don't match up. It's slowing down. So now let's finish up this number line example. So I've plotted a number line for x double prime of t, and we see that x double prime of t is a constant. It's just 6. What is the sign? It's positive. So from 0 all the way to infinity, it's always going to be positive. So now we have to take a look at 1, okay? Because remember, 1 it's the turning point for the velocity. It's the turning point for the position graph. The velocity at that point is 0. Okay? So since from 0 to infinity for the acceleration graph, it's positive. Same for 0 to 1. 0 to 1, that includes 0 to infinity, of course. So it's positive here. Okay, it's positive everywhere, basically everywhere. But then for the velocity graph, it's negative. It's negative here. It's positive here. They don't match up. They don't match up. And therefore, the object is slowing down. However, from 1 all the way to infinity, for the velocity and the acceleration graph, they're both positive. They're speeding up. Capiche? So therefore, we can say that the graph of 3t squared minus 6t plus 4 will look something like this, where from 0 to 1, the function is slowing down. It's basically going to the left, right? Because we said that the velocity was negative from 0 to 1, so it's going to the left, and the left we would say is going down on the y-axis side. And for after 1, it's speeding up, right? The velocity was positive, the acceleration was also positive. The acceleration is positive the entire time. Okay, it's just the velocity that and the direction of the velocity, that's what would give it this the parabola shape.